Hey folks, today we're going to talk about or introduce rolling. Good news is there's not a whole lot new here. The interesting part is though we'll be combining material from the previous chapter and then from prior chapters to that. So we're combining stuff when we're doing rolling. There will be some new aspects, obviously, that we'll talk about, but um, a lot of the concepts we already know. So on the picture here that I've drawn, a very, very complicated picture, I know. Imagine that is a wheel or a disc rolling along the ground. And let's assume that it's rolling with an omega. All right, so it's got an angular velocity. Okay. So first off, the wheel has a center of mass, right there. Okay. And with respect to omega, how fast is that center of mass moving? So, like, in other words, this were, let's say, a car wheel. This is what your speedometer would say, all right? Because that's where your axle of your car is attached to your wheel. So, what's that speed? Okay. Well, first thing I'll point out is what's the axis of rotation of this wheel? Most people, when you first look at this picture, they're going to say the center of mass. That's the axis of rotation. That's not quite what we have here. What part of the wheel at this moment is not moving? Well, the part of the wheel that's in contact with the ground is not moving. So that is actually our axis right now. In other words, what you can pretend is this wheel is spinning about that axis, and it's almost as if it's going like this, a quarter turn later, and this a half turn later, and this three-quarters of a turn later. It's as if it's pinned at its edge and rotating about that pin. Okay, so a lot of what we're going to do today is we're going to pretend the wheel's doing that. It's the same idea. Okay, so what is the velocity of the center of mass? Well, the distance from the axis to that point is simply r. So VCM is simply equal to r omega. Okay. Now, on a side note, what if I asked you about the very top of the wheel? Well, that actually has a greater linear velocity. It would be 2 times the velocity of the center of mass, or 2r times omega. So that part of the wheel is moving much faster as you roll. Okay. And again, the part of the wheel that's in contact with the road is not moving at all because it's in contact with the road. Okay. Now notice that this is a little different than last chapter. Last chapter would say you had a disc spinning about its center. Well, the velocity we usually had you find then was the velocity of a point on the rim, which would be r times omega again. But it's a velocity of a different part of the wheel. Okay, so it's a similar idea, but a different part of the wheel, because in this case, the wheel is just spinning, whereas in our case, the thing is rolling, which is a different kind of motion, or it's an addition of motion. Similarly, if the wheel is speeding up or slowing down, the center of mass will have a linear acceleration. That'll be r alpha. Okay, and some review materials from previous chapters. We know that net force is still going to equal ma. That's Newton's second law. In rotation, Newton's second law is net torque equals I alpha. That's not going to change. And when we have an object and it's not spinning about its center of mass, but some other axis, we can find the moment of inertia about any axis by taking the moment of inertia of the center of mass plus the mass of the object times the distance from the axis to the center of mass squared. That's called our parallel axis theorem. We're going to be using that quite a bit. Now, what if I ask you what the total kinetic energy of this wheel is as it rolls down the road? Okay, well, let's start with comparing that. Imagine I had a second wheel, same mass and everything, moving at the same velocity, but let's pretend that it's on ice and it's not rolling. It's just flat out moving or sliding to the right. Okay, so the kinetic energy of that thing, so since it's not rolling, it's just sliding to the right, the kinetic energy of that thing would be 1/2 mv squared. How about the rolling wheel, the one in black? Well, it's still moving to the right with this at that velocity, so it's going to have 1/2 mv squared, but it's also spinning. So it's in addition, it's going to have some 1/2 I omega squared. So the wheel in black there is actually going to have more overall kinetic energy than the wheel in red, because the wheel in red is not actually spinning, it's just skidding along the ground. Okay. So for the rolling wheel, the one in black, let's talk about the total kinetic energy. Okay, well, one way to do this is it's kinetic energy rotational about our axis. It's as if the object is spinning around that axis, which would be 1/2. You'd have to use parallel axis theorem to figure out the moment of inertia. So I'm going to write that out here. ICM plus m, and the distance from the axis to the center of mass is r squared, and then you'd have omega squared. Okay. Now I'm going to separate those two terms out. So the first term is 1/2 ICM omega squared. The other term is 1/2 times mr squared omega squared. All right. So this first part would be if the wheel were just spinning and not actually moving laterally, that would be your total rotational kinetic energy. But we also have this term added on now because we're moving to the right. Now, one other thing I know is omega is equal to V over R, right? I'm just looking at this VCM equation and solving it for omega. I'm going to sub that in for omega here. And by the way, this is VCM, okay? So we end up with 1/2 ICM omega squared plus 1/2 times mr squared times, if I square this would be V squared over R squared. And you might notice that the r's drop out. And look what we get. We get 1/2 ICM omega squared plus 1/2 m V squared. Okay. And you can put VCM here if you'd like. All right, so what is this telling us? Okay, this is telling us that another way to figure out the total kinetic energy of that rolling wheel is to add up its kinetic energy rotation about its center of mass and its kinetic energy, we call this translational, the first kinetic energy you guys learned, 1/2 mv squared. So what we're going to do is we're going to add up the effects of the spinning and the moving to the right. That's these two effects right here. Okay. So what we can say is we can say that the total kinetic energy of an object is equal to its kinetic energy rotational about its center of mass plus its kinetic energy translational. Okay. For this particular example, how does the total kinetic energy compare to just a translational? Okay. Well, remember omega is equal to V squared over R, and ICM for a disk is 1/2 mr squared. So over here, I'll play with that. So on the left, we have 1/2, moment of inertia center of mass is 1/2 mr squared. Omega is V over R, so this becomes V squared over R squared. And then plus we have the second term, which is just 1/2 m V squared. And you'll notice that again, the R's drop out here on the left side. So you get 1/2 of 1/2, that's a quarter mv squared plus 1/2 mv squared, which is 3/4 mv squared. So if the disk is just sliding along the ground, it's only going to have 1/2 mv squared kinetic energy. If it's rolling, it's got a total of 3/4 mv squared kinetic energy. So it's got 50% more energy if it's rolling. Different objects have different percentages depending on their moment of inertia equation. Okay. So from here on in, what we're going to be doing is we're going to be, when something is rolling, whether it's along level ground or down a ramp or anything, when we talk about the kinetic energy of the object, we're going to sum the rotational energy about its center and the translational kinetic energy. The next thing we'll do is we'll do some examples and use this idea to solve problems. I hope that was helpful, and thank you very much.